Hello learners, welcome to Unacademy, and today's class we are going to learn about what is a dipole and what is electric field due to a dipole. Alright, with that note, let's begin. My name is Mohana. I'm a physics educator here with Unacademy. You can follow me on my Telegram channel, and this, if you see, this is the common ICSE and ISE both channel, so you can follow this channel as well. Alright, so if you see what is an electric dipole, very simple definition. If you take two charges such that these two charges should have opposite polarity, that is, if one is negative charge, another has to be a positive charge, but the magnitude of these two charges has to be the same. So for example, let's say this is -2 microcoulomb. So this charge, the other charge has to be +2 microcoulomb. And if these two charges are separated by a small distance over here, then we say that is nothing but an electric dipole. Alright, good evening Akshay. So instead of r, most places if you see the distance between the two dipoles, we take it as 2a. Alright, so an electric dipole is very simple. You have two charges, one is positive and another is negative. They are separated by a distance and the charge magnitudes are same. Okay, so if you look at the electric field lines in this case, right, so if one charge has around, for example, around 100 field lines, if this negative charge has around 100 field lines, the positive charge will also have around 100 field lines. Now, when you keep these two charges at some distance, what tends to happen to the electric field is they tend to bend. That is, the electric field lines tend to start at the positive charge and end at the negative charge. Okay. So now what we want to do, we want to measure what is the electric field field intensity or the strength of the electric field of a dipole. Before we do that, we are going to learn one more topic, that is electric dipole moment. Electric dipole moment, it just measure the strength of an electric dipole. Alright, and if you see, it is a vector quantity and its direction is always from a negative charge to a positive charge. Now, obviously, it measures the strength of an electric dipole, right? So, how do we measure it? The formula for it is very simple. Okay, electric dipole, if you see, by definition, it is either you take one of the magnitudes. Very simple. Why? Because if this is minus 2 microcoulomb, I said this is +2 microcoulombs. Magnitude wise, they are same, right? So, for example, even if you're taking the magnitude wise, they are same. It's just that one is a positive charge and another is a negative charge, right? So, you take one of the magnitude of the charges, and what is the distance between these two charges over here? Okay, distance over here you can take it as around 2a. You can take it as d, but most books take it as 2a over here. Alright, so this is basically electric dipole. And if you see electric dipole again over here, this particular yes Akshay, you can write it as q into d, provided this distance instead of a, if you take 2a, if you're taking it as d, you can write dipole moment is nothing but q into d. So if you see its unit, it's nothing but for charge, the unit is coulomb. For distance, the unit is meter. So dipole moment is coulomb meter. It's a vector quantity. Charge is actually a scalar quantity, right? This distance can be taken as a position vector, right? So here could be a vector quantity. So we end up getting dipole moment as a vector quantity, and its direction is always from negative to positive. Okay. All right. Now with this, we just want to find, okay, given such a charge, what we are going to do is, we want to find how would the field intensity be if you move along this line charge over here. How would the field intensity be? And then if you see, if you go perpendicular to these two charges, how would this field intensity be? Okay, this is what we want to find. We want to find electric fields in these two cases. Alright, the first case we are taking is electric field at an axial of a dipole. That is, let's take two charges, one is -q and +q, and if you see, along the line joining these two charges, that is, if you move along the axial line, okay, and at some point P over here, we want to find what is the electric field. Okay, for example, in this picture, if from here if you're going some point over here, some distance over here at point P, we want to find what is the electric field. Okay, so now let's so for this at this particular point we want to find the electric field and the distance between these two charges. If you see, that is going to be 2a. Okay, so let's do this. Let's take this center point to be O. Okay, then this distance is going to be a and this distance is again going to be a. Now total distance between them, what happens to total distance between them? It becomes 2a. Okay, now from the center to this point P, let's take this as r, this distance as r. So knowing just these quantities, okay, so over here you have to remember from the center of the dipole to the point P over here, this distance is r. Now just knowing these quantities, let's see what is the electric field. Alright, now when we see when we actually try to find the electric field at this point P over here, it is because of this positive charge and also the electric field because of the negative charge, right? And if you see at this point over here, these two electric field between these two charges, we have to add the electric field between these two charges present, right? So first let's see what is the electric field. Okay, electric field due to the positive charge over here. Due to the positive charge, if you see, okay, very simple, electric field equation is given by 1 by 4 pi epsilon naught q divided by distance square. Okay, sorry, it's q divided by distance square. What is the distance? So very simple, the distance over here we want to measure the distance, that is from this point P to the charge q. Okay, in other words, how are we measuring at this point P what is the electric field over here? We tend to introduce a test charge. Okay, test charge has a very small mass, so the field of the test charge doesn't disturb the field of this dipole over here. Okay, so introduce a very small test charge at this point. Okay, and if you see, right, we introduce a very small test charge at this point over here. Okay, now if you see the electric field between them, okay, what is the distance? This distance we want. Okay, we don't know this particular distance over here, but we know this distance is r, we know this distance is a. So if we do r minus a, we'll end up getting this distance. Okay, and this distance is nothing but, this particular distance is nothing but r minus a, right? This distance is r minus a. So here we end up having r minus a, okay, r minus a the whole square into, we have a dipole moment. So we will write dipole moment's unit vector, okay, that is p cap over here. Okay, now obviously we found this. Now what would be the direction? What would be the direction of the field at this point? Now this field, this is a positive charge. This is also the test charge, unless otherwise specified, it's always a positive charge. Like charges will repel each other, right? So at this point electric field would be somewhere along this direction. Okay, in other words, if it's a positive charge, electric field lines are pointed always radially outwards from the charge, right? So in this point electric field lines are in this direction. Now similarly we are going to find what is the electric field because of the charge minus q over here. Okay, that will be nothing but 1 by 4 pi epsilon naught. Okay, and the charge over here we have is basically minus q divided by what is the distance. Now the distance between these two charge, if you take, it is from this point over here. Okay, this is from this point over here to this distance. Alright, so at this distance we know is r, this distance we know is a. So this entire distance that we are taking will be nothing but r, plus a. Okay, so substitute that in the electric field equation, we will end up getting E is equal to 1 by 4 pi epsilon naught minus q divided by r plus a the whole square into p cap. Okay, again at this point we want to find what is the direction of the electric field. Okay, now this is a positive charge, the electric field at this point, okay, if you have a charge, the electric field lines will be pointed radially outwards everywhere from this point over here. Okay, and this point over here, for negative charge, the electric field lines are pointed radially inwards, right? So from here, if you see, from here this charge is pointed radially outwards, but here the charge is pointed radially inwards. So electric field is in this direction. In other words, if you want to see, this charge experiences a force towards the negative charge, right? So electric field lines will be in the direction of the electric force. So this charge will be attracted towards this positive charge. So this field will be, the field will be in the direction of the force, right? So here what we have another vector which is actually EQ, which is in the opposite direction, right? Okay, now if you see from here, if you see what is the, we want to find what is the electric field along the axial. Okay, so along the axial line, okay, electric field along the axial line, electric field at this point, okay, electric field at this particular point over here is because of this positive charge as well as because of this negative charge. So according to superposition principle, what we would do, we would add both these charges, okay, charge because of the positive charge, okay, electric field because of the positive charge, and electric field because of the negative charge, okay. Axial is because of these two charges. Now let's substitute that in this equation. We have this is nothing but 1 by 4 pi epsilon naught, okay. 1 by 4 pi epsilon naught. For positive charge we have Q divided by R minus A, right, the whole square into P cap plus, right, 1 by 4 pi epsilon naught. This charge over here is minus Q divided by R plus A the whole square into P cap. Now minus is over here, we can bring it out, right? So this positive sign over here would tend to become negative. Now let's try to take all the common factors outside. Okay, so the common factors on one side we have is 1 by 4 pi epsilon naught and the charge Q, that is constant. Then we have on the other end 1 by R minus A the whole square, right, minus 1 divided by R plus A the whole square into, we have P cap, okay, this dipole moment as well. Now let's look at this quantity. I'm just going to solve for this quantity separately, okay. So here we have one quantity, that is 1 by R minus A the whole square plus 1 divided by R plus A the whole square. Let's solve for this. Very simple. Here we are going to cross multiply. We'll get R plus A the whole square plus R minus A the whole square whole divided by R minus A the whole square, okay, into R plus A the whole square, right. So this over here, okay, let's just look at the denominator, R minus A the whole square, okay, R minus A the whole square into R plus A the whole square. For a moment let's forget the square terms over here. So this is of the form x minus a, right, yes Akshay, we are going to use the formula. This is of the form x minus y into x plus y, which is nothing but x square minus y square, right. So R minus A, R plus A is of the form, okay, R square minus A square. Now along with this what we have, we also have a square term. So this term, okay, one second, here I wrote the brackets outside, one second, okay, we have R square minus A square. Along with this we have a square term, so this term over here will tend to get squared as well. So in the denominator what we have R minus A the whole in the denominator term, it is denominator term. Now if you see, it is reduced to R square minus A square the whole square, okay. So this particular term is reduced, right. Yes Akshay, thank you for the formula. Now this is the denominator term. We are done with this term. We have reduced this term. Now let's look at the numerator, okay. Let's expand the term. So initially what we have first over here, we have R plus A the whole square, okay, plus R minus A the whole square, okay. Very sorry over here, it will not be positive, I made a mistake, it will be a negative, right. We said 1 minus A, this is a negative quantity, okay. So very simple, expand this term over here. R plus A is nothing but R square plus A square plus 2AR, and R minus A is nothing but R square plus A square minus 2AR, okay. Now take this within take the now let's take the negative side into the bracket, right. Right, so in this case you will end up getting minus R square minus A square plus 2AR. So plus R and minus R gets cancelled, A square and minus A square gets cancelled, these two terms tend to get added up, so we get 4AR. So on the numerator we have 4AR over here. Okay, so finally we have reduced this particular term to 4AR. Okay, finally we have just reduced this particular term to 4AR. Now let's write this. This is nothing but Q divided by 4 pi epsilon naught, and here we have 4 into A into R divided by, okay, divided by R square minus A square the whole square, okay, into P cap. Now remember the definition we had for dipole moment. We said, okay, dipole moment is nothing but, okay, dipole moment is nothing but that P is nothing but 2A into Q, charge into the distance. Distance in this case we have taken as 2A. Distance between the two charges we have taken as 2A. Okay, so 2A into Q, that is P. So let's see if we can make that term over here. So here we have 1 by 4 pi epsilon naught. Okay, then if you see we have this term, let's make it as 2 into, okay, 2 into R as one term, and then if you see we'll have 2A into Q. Okay, so divided by, this I'm splitting it as 2 times 4, we are splitting it as 2 times 2, and then we have a R, so 2R into 2A, the remaining terms, into Q. Okay, divided by R square minus A square the whole square into P cap. Now from here what would happen? This term over here tends to become P, okay, which is nothing but the dipole moment. Alright, so from here we have one term, that is 1 by 4 pi epsilon naught 2RQ divided by R square minus A square the whole square. Right, now let's say this distance is very, very small. For example, let's say, for example, okay, for example, let's say R is equal to 10, let's say 10 centimeters, okay, any unit, right, let's just take it as centimeter. Let's say this 2A, okay, 2 times A, this distance over here is actually equal to 0.1 centimeters. Okay, now when R square, when you square this term over here, right, when you square this term over here, when you square R, okay, 10 square will become 100. Okay, but when you square this term 2A square, okay, the distance square, okay, or A square over here, I'm really sorry, this A square over here, even if you're taking it as just A over here, okay, when you square A square over here, not even this distance, just this distance is 0.1 centimeters, this term when it squares, it will become 0.01, right, it becomes much more smaller. When compared to 100 centimeter, this value over here is very, very small, right, it's negligible. So we are going to take one more assumption over here. What we are going to say is, we are going to say when R is extremely, okay, when R is extremely larger than A, okay, this term A square can be neglected. So if you neglect the A square term over here, okay, so what you will tend to have, okay, what you will tend to have, you will have R square the whole to the power square, okay, R square the whole square, which is R to the power of 4, right. Now R and this R in the numerator, we can actually divide these two, right. So this will end up giving you RQ, right. So that's it. This is electric field, okay. This what we got over here is electric field at an axial point at a point P, that is basically at a distance R, okay, from the center. So what we are seeing, electric field due to axial is inversely proportional to, E is inversely proportional to R square, okay, E is inversely proportional to 1 by R cube, sorry, not square, R cube, okay. So that's the electric field at this point over here. Now this positive charge obviously is closer than the negative charge, so final total electric field, if you see, it will be along this direction, okay. That is, the electric field in this case will act along the electric field at any axial point, okay, will act along the dipole axis from negative to positive. It will always be in this direction, okay. The axial point, the final vector, it will always be in towards this direction. Alright, so this is electric field at an axial point of a dipole. Now let's see what happens if you are looking at the equatorial point. Now initially we went around, let's say 1 meters. Okay, r is equal to 1 meter and found p at this value. At this point p we found what is E. Now we'll go the same 1 meter from this center over here. Initially from the center we went 1 meter. Now we'll go 1 meter from this point over here. Okay, and we'll find what is the electric field at this point, that is perpendicular to the field. Okay, very simple over here. Okay, again the same, these two, the distance between these two is actually 2a, so the center point will be O. This distance is a, right? So obviously this distance will again be a. Now we're going to choose a point from the center point O. We are going to choose a point P at this the same distance as we chose for the earlier case. Okay, this distance over here, this is nothing but r. Alright, now think about it. What will be at this point over here, what will be electric field line because of this positive charge, right? So because of the positive charge, at this point P, if you introduce a test charge, this is positive, this charge is also positive. So force acting it will be in this direction, meaning the field lines because of the electric positive charge will be in this direction. So if we write that, electric field for this case, for the positive case will be nothing but 1 by 4 pi epsilon naught, right? Q divided by, okay, Q divided by the distance. Now we have to do a bit of trigonometry in this case. Why? We want to find what is this distance over here. We know this distance and we know this distance over here, right? So what we are going to do, let's look at this as a right angle triangle. Okay, so this distance we know is r, this distance we know is a. We want to find what is this distance. Okay, this distance over here is nothing but if you're using Pythagoras theorem, what would happen? Hypotenuse, this distance over here, let's call it as x over here. Okay, x square is nothing but r square plus a square. So x will be nothing but root of r square plus a square. So this distance is nothing but root of r square plus a square over here. Okay, so if this distance is r square plus a square, means substitute that in the equation. In place of distance, we have root of r square plus a square, the whole square. So square root and square tends to get cancelled. So we have one equation. Okay, and this is nothing but r square plus a square. Okay, now from this point over here, okay, what we are going to do, what is the electric field at this point P because of the negative charge over here? Okay, so this distance is r. Okay, this distance is r, this distance is a. So this distance will again be the same as the previous case, that is nothing but root of r square plus a square. So electric field because of the negative charge, if you take, it's nothing but equal to 1 by 4 pi epsilon naught, the charge q, okay, we are just taking the magnitude of the charge, divided by r square plus a square. So what are we seeing over here? The magnitude wise they are both same, but this point charge is a positive quantity, this is a negative quantity, right? So this charge is a negative. So in this case the electric field lines will be pointed along this direction. Okay, so what we are seeing, whatever is the charge, electric field because of the positive charge, we are having electric field at this point because of the positive and negative charges are same. Alright, but if you see they are at an angle, so we have to resolve these two vectors. It's a vector, right? So we have to resolve these two vectors. So let's see, let's actually let's try to resolve these vectors. So we have okay, so we have one vector along this direction, another vector along this direction, right? This is positive electric field because of positive quantity, and this is electric field because of negative. Okay, now let's resolve these two vectors. If you resolve them, right, for the positive quantity we'll get these two vectors over here, right? And from here what we see, let's say this angle over here is theta. Alright, so this value of this particular vector we have in this side over here. Okay, let's just take this triangle, that is, this is E, the positive quantity, right? And we have another vector, let's say this is for the positive along the vertical, and this is for the positive along the horizontal. Okay, so in this case we have two vectors and this angle is theta. Now we can move this particular vector to the other side. right? 1 second. Okay, so this vector is EQ. Okay, now if you want this side, let's for example as of now take it as x. It becomes very easy. Okay, cos theta is nothing but this value of x divided by hypotenuse, which is nothing but this EQ over here. So x is what? The electric field, magnitude of the electric field along the hypotenuse, this value into cos of theta. Okay, so this will be E, this particular quantity over here will be nothing but, okay, EQ cos theta. Now if you take this as y over here, sin theta is nothing but base, okay, perpendicular by hypotenuse, which is y divided by this value, magnitude of this side over here, which is y is nothing but EQ into sin theta, right? This is nothing but EQ into sin theta over here. Okay, similarly you take for the other vector over here. Alright, try and resolve this component. Let's say this is again theta. You will again get, okay, you will again get this side as EQ. Okay, in this case it is minus. Okay, this will basically be minus in this case, but again you will end up getting, this will be a positive quantity. Okay, EQ, E minus Q cos theta and E minus Q sin theta. If you look at the component, that E minus Q and E plus Q sin theta over here, they are equal in magnitude but they are opposite in direction, they cancel out, and this quantity over here, EQ cos theta, they tend to get added up. Okay, so if you see what is the resultant quantity over here, the resultant for the equatorial plane will be along this direction. It will be EQ, this is basically equatorial. Okay, this is for the equatorial, this will be the direction of the resultant. Okay, this is angle theta again, and this is again angle theta. Okay, this is along the equatorial. Now, okay, so for the equatorial plane, what we are seeing, for the equatorial plane, what we end up seeing, that, okay, this value is nothing but equal to, okay, so in this value, if you see, it is nothing but equal to this E minus Q, that's what we got, right? E minus Q cos theta plus E plus Q cos theta. Now we will get a minus sign over here. Why? Electric field is in this direction. Final electric field is in this direction. But dipole moment, if you take, is in the other direction. Because they are opposite to each other, we get a negative sign. Okay. So let's do this separately. Let me quickly do this separately. That is equatorial phase, if equatorial field, if you see, is nothing but minus of E minus Q cos theta. Okay, we are just adding those two vectors, right? Components that are parallel to the dipole axis. So this is basically plus Q cos theta into P cap, minus sign simply because this positive quantity, this electric field, because of this electric field and dipole moment are in opposite sides. Now this is nothing but equal to what? We said magnitude wise these two are same. This is nothing but minus 2. We can substitute for any one, right? Why? Because we said magnitude wise they are both same. E plus Q and E minus Q are both same. Okay. Now let's substitute for E plus Q. What is for E plus Q over here? Or E minus Q over here? It will be nothing but, that value is nothing but 1 by 4 pi epsilon naught. Okay. Q divided by R square plus A square. Now into, okay, we end up having cos theta. So from here we have to find cos theta. Okay, now think of taking this angle over here. This is like a right angle triangle, right? So whatever this angle is, this we could see an inverted triangle over here also, right? So whatever, okay, you can take opposite sides are equal. If this is a straight line, and if this angle over here, okay, and we have two parallel lines and the line passing through the center. If this angle is theta means, then if you see, this angle will also be theta. Okay, now if this side is A means, this side length is also A. Okay, now instead of taking for this particular triangle, instead of saying we are taking for this triangle, because these two sides are opposite, we can take for this particular side, because this length is r and these two are parallel straight line and there is a line passing through them. So this angle is theta, this angle is also theta. Now if you see from here, we have a right angle triangle, and if you find cos of theta in this case, okay, if you find cos of theta in this case, it will be what, this direction, that is basically the perpendicular, sorry, base over here, that is A, divided by hypotenuse. Hypotenuse is nothing but this distance. This distance is nothing but root of r square plus a square. Okay, now we will substitute the same over here. This is nothing but a divided by root of r square plus a square, okay, into we have p cap. Now think about it, we have minus, okay, 1 by 4 pi epsilon naught. Again we have a quantity 2a into q, okay, divided by these two terms. If you see, we have r square plus a square to the power 1, and if you see, this is to the power 1 by 2. So we can add them, right? This is to the power 1, this is to the power 1 by 2. If you add them, what would you end up getting? In this case, this 1 plus 1 by 2, this will end up becoming 3 by 2. Okay, and this quantity we have 2a into q, this is nothing but, this quantity is nothing but 1, we have 1 by 4 pi epsilon naught, and we have a p cap also, and if you see, this quantity is nothing but p divided by, okay, again we have r square plus a square, the whole to the power 3 by 2. Now think about this equatorial line. Again we are doing the same assumption. What we are saying, this distance r, let's say this distance is larger than this a value over here. Similar assumption as we did earlier. If r is somewhere around 100 units and let's say a is around 0.1 unit. Okay, this distance a is 0.1 unit. So when r becomes r square, it becomes 100 square, but a becomes 0. For example, if you are taking it as 0.1, it begins to become 0.001. Right, when compared to 100 square, 0.001 is very small quantity. Okay, so when r, okay, when r is extremely greater than a, we can ignore a square, we can neglect a square. Then what we will end up having, we will have 1 by 4 pi epsilon naught, okay, into, right, p divided by, we can neglect r square, so we will have, okay, we will end up having r square plus a square is actually neglected, right, because we are saying r is much more greater than a. Then you will have whole to the power of 3 by 2 p cap, right. This again 2 gets cancelled over here, all you will have is r cube. Okay, so this gives us the electric field along the equatorial phase over here, okay, which will be 1 by 4 pi epsilon naught p divided by r cube. Okay, so if you see the electric field, this is not the right value, this is for axial, okay, this is basically for axial, this is for equatorial over here, okay. So again along the equatorial also, what we are seeing, that this value is equal to, this electric field is inversely proportional to the cube of the distance, right, which means if you go further away from the field, okay, if you go further away from the dipole, the field reduces. So from the center, if you keep going further away, the field tends to reduce. So along the axial, from the center, if you go a certain distance, okay, let's say a certain distance r, we find the axial equal, this electric field along the axial to be 1 by 4 pi epsilon naught, okay, 2p divided by r cube into p cap, okay. Now from here, let's go the same distance r. If r is 10 units, you go 10 units in this point also, okay. And along this point, if you see what is equatorial, we end up seeing this is 1 by 4 pi epsilon naught, just p divided by r cube into p cap. So what we are seeing over here, this value is nothing but equal to twice 1 by 4 pi epsilon naught p divided by r cube into p cap, which is nothing but twice equatorial. What it means is, along the axial, the field strength is twice the equatorial point, or the electric field of a short dipole at a distance r along the axis is twice the electric field at the same distance along the equatorial line. That is, okay, for example, let's say at this point over here, electric field strength, I'll give a, for example, electric field strength along the axial at this point, for example, let's say the electric field strength is around 5 Newton Coulomb, okay, or sorry, 50 Newton Coulomb. Now from here you go another from here, let's say the distance you went is around 10 units. From the center again you go 10 units in the equatorial plane or perpendicular to this dipole. Okay, at this point if you see what is the electric field strength along the equatorial, it will be around only 25 Newton per coulomb. Okay, so this strength over here is half of what is the strength at the axial point over here. Alright, so that's it. This is all about electric field due to a electric dipole. Okay, and I'll see you all in another class. So if you like the video, please share it among your friends, subscribe to the channel and click on the bell icon so you can get notification before any class goes live. Alright, see you all in the next class. Bye.